Hello, everyone, and welcome to the CTAIO Labs podcast. I'm Thomas Palmer, your host, founder of CTAIO.dev, the destination for future tech leadership. For anyone new here, I spent over 2 decades in tech as a hands-on developer, engineering manager, CTO, and CIO, inside companies like Apple, Google, Netflix, Adidas, and McDonald's. Today, I advise mostly Fortune 50 enterprises at that critical intersection of technology and AI. On this podcast, we get hands-on, real, pragmatic, real-world lab experiments at exactly that intersection. To secure your weekly AI edge, subscribe to my newsletter at CTAIO.dev. That's where new episodes drop. And if you'd like to say hi or ask about advisory work for your enterprise, head to Palmer.net. A response is always guaranteed. Now, this kicks off Season 2, Agentic Orchestration. Season 1 was building my AI twin, where we clone my voice, my face, and my brain. This season we go to where the real engineering is, orchestrating AI agents in production. And we start with the question every engineering leader is asking right now. Which agent framework do we standardize on? So I built the same 3-step agent in 6 of them. LangGraph, CrewAI, AutoGen, OpenAI Swarm, Pydantic AI, and LlamaIndex. Here's the spoiler. 2 rows to the top, and neck, LangGraph and CrewAI. Which one wins comes down to one thing about your team. What follows is a deep dive generated with Notebook LM based on the full lab report at CTAIO.dev. I'll be back at the end to wrap it up. Enjoy.
So imagine this. It is 3:00 a.m. on a Sunday. You are the CTO of a mid-sized tech company, and your phone just starts vibrating right off the nightstand.
Oh, man, the absolute worst feeling.
Right, and it's your company's brand new AI agent, the exact same one that had this flawless, beautiful demo for the board last month, the one that was supposed to automate your entire inbound data pipeline. Well, it is just hallucinated an infinite loop in production.
Yeah, which is just a nightmare. It's rapidly firing API calls to some external service, failing, and then retrying with just increasingly garbled JSON payloads.
Exactly. And it's racking up like a $5,000 OpenAI bill in the span of maybe 20 minutes.
And the real kicker here is, because of the specific orchestration framework your team chose to standardize on, you log into the monitoring dashboard and realize you have absolutely zero visibility into the state of the agent.
Wow, nothing.
Nothing. You have no idea what prompt triggered the loop, what data was holding in memory when it crashed, or even how to stop it without just taking the entire production server offline.
I mean, welcome to the absolute worst nightmare of 2026.
Yeah.
This is the exact scenario keeping engineering leaders awake right now. Because look, the prototype phase of artificial intelligence, it is officially over.
No, completely over. We are so done with the flashy Twitter demos and, basic chat bots.
Right. The mandate from the CEO has come down. They're saying, we need autonomous AI agents running in production, and they need to actually be reliable. But that leaves you, the listener, facing this massive multi-million-dollar architectural bet. Like, which AI agent framework do you actually standardize your entire engineering organization on?
It is a terrifying decision. I mean, you are essentially pouring the concrete foundation for your company's infrastructure for the next 5 years. But you're choosing between frameworks that, in some cases, literally didn't exist 18 months ago.
Yeah, the landscape is shifting so fast that the docs are out of date by the time you finish reading a page. Which is exactly why today's deep dive is just so critical. We are tearing into the highly anticipated Season 2 opener from Thomas Palmer over at CTAIO.dev. Now, if you followed his work, Season 1, which was called Building My AI Twin, was this fascinating, almost sci-fi exploration where he cloned his voice, his face, his knowledge base.
Yeah, that was wild.
It was. But for Season 2, which he titled Agentic Orchestration, he has shifted gears entirely. He moved from that bespoke personal cloning experiment to the gritty, unforgiving reality of enterprise deployment.
And what I love is he is doing it strictly as an honest practitioner. No hype words, no marketing copy. We are looking for real developer experiences, actual computational costs, and real catastrophic failure modes.
Right. So let's talk about the methodology here, because this is where Palmer really separates himself from the noise. Usually when evaluating a framework, developers will, go to the official website, clone the repository, run the highly optimized Hello World tutorial.
And when it works perfectly in 5 minutes, they think, oh, this is the one.
Exactly.
But those tutorials are just the showroom floor. They're heavily manicured, frictionless paths designed specifically to hide the framework's inherent architectural flaws. They don't represent what actually happens when you ask the framework to do something it wasn't explicitly built to do.
Which is why Palmer didn't do that. His experiment is just brilliant in its brutality. He decided to build the exact same 3-step research agent across 6 different orchestration frameworks.
I love this setup.
It's so good. He forced all 6 of them to execute the identical sequence. So step 1, perform a web search to fetch raw data. Step 2, process and extract specific financial metrics from that data. And step 3, synthesize and format a final output report. He put them all through the exact same mud pit, completely apples to apples.
And that identical agent constraint is really the only way to expose true architectural friction. We don't care how shiny the abstraction layer looks in the showroom. We want to know what happens when you force it to handle asynchronous API calls, complex nested JSON parsing, rate limit backoffs.
Right, like which framework gets bogged down in boilerplate, or which one obscures the error trace when things break under the pressure of a non-deterministic language model.
Exactly.
So we are going to line up these 6 vehicles and inspect them. But we're not just going to read off a list from 1 to 6. We need to understand this landscape by looking at the spectrum of abstraction. In software engineering, abstraction is everything, right? It's the distance between the metal of the machine and the human intent.
Yeah. Do you want to wire the circuits yourself, or do you want to just press a button and trust the machine to do it?
Exactly. And in the world of AI agents, that abstraction spectrum is incredibly wide right now.
It really is. On one end, you have frameworks that force you to write rigorous, strictly typed code where you control literally every variable. And on the other end, you have frameworks where you just write English sentences telling the agent what its personality is, and the framework tries to magically infer the code.
It's wild. So let's start at the very bottom of that abstraction stack, right closest to the metal. The framework that demands the most rigorous engineering discipline, Pydantic AI. Now, for anyone listening who manages Python backends, the name Pydantic immediately carries weight.
Oh, absolutely. It's the gold standard for data validation in Python.
Right. And Pydantic AI takes that exact philosophy and applies it to the agent layer.
It is arguably the most anti-magic framework on the board here. Its entire core identity revolves around extreme type safety. Let's actually talk about how that works under the hood, because it addresses a really fundamental problem with large language models.
Okay, lay it out for us.
Well, at their core, LLMs are just text prediction engines. They generate raw strings. But standard enterprise software doesn't run on raw strings. It runs on strictly typed data objects. Integers, booleans, nested dictionaries with very specific schemas.
Right, like if my database is expecting a user's age as an integer, and the LLM decides to be helpful and outputs the string 25 years old with text, my database query just crashes.
Precisely. And the historical way developers tried to fix that was by writing incredibly fragile prompt engineering, like literally begging the LLM, please only output a valid JSON object. Do not include any conversational filler.
We've all been there. Do not output Markdown.
Yes. But Pydantic AI changes that paradigm completely. It uses constrained decoding and strict schema injection at the API level. So you define your tools and your expected outputs as rigorous Pydantic models.
So you are writing standard Python classes. Like you define a class called financial report, and you specify that revenue must be a float and company name must be a string.
Exactly. And the framework essentially forces the LLM to conform to that mathematical shape. If your backend engineer used to strict type checking, where the compiler refuses to run unless the data matches the exact shape, Pydantic AI offers the lowest impedance mismatch to your existing workflow.
It just feels like Python.
Yeah, it doesn't feel like you are learning some esoteric new agentic language. It just feels like you are writing rigorous, bulletproof Python.
That sounds incredibly appealing for a team that values stability. But as we move slightly up the abstraction spectrum, we hit the framework that has arguably sucked the most oxygen out of the room this year, which is LangGraph. Now, LangGraph has a very distinct philosophy. It doesn't just treat the agent as a sequence of prompts. It models the entire agentic workflow as a directed graph.
Right, and this is where we introduce the concept of finite state machines into AI. In LangGraph, you are explicitly defining nodes and edges. And we should probably clarify what those terms mean in this context, because the way they do it is brilliant.
Free to.
So a node in LangGraph isn't some abstract, magical AI concept. A node is just a standard Python function. It takes the current state of your application as an input. It does some work, which might involve calling an LLM or querying a database or running a calculator, and then it returns an updated version of that state.
Okay, so if the nodes are the workers, the functions doing the actual lifting,
Yeah.
what are the edges?
The edges are your routing logic. They are the conditional statements that evaluate the state to decide which node runs next. For example, you might have a node that evaluates the quality of a generated report. The edge connected to that node contains logic that says, if the report quality score is below 7 out of 10, route the flow back to the research node. If it is 7 or above, route it to the publish node. You are explicitly drawing the pathways the data can take.
Which gives you massive control. But hold on, if LangGraph nodes are really just standard Python functions and edges are just conditional logic, why do I need an entire framework for this? I mean, can't I just write a standard while loop in my code and throw some if-else statements in there? Why adopt this massive complex dependency just to route functions?
That is the exact question every senior engineer asks before they try to build an agent from scratch. And it's a great one. You absolutely can build it with while loops right up until the moment you need streaming, persistence, and human-in-the-loop interruption. Yeah. LangGraph's architecture isn't just about routing. It is about state persistence. Because it models the flow as a graph, it can save the entire state dictionary to a database at every single node transition.
Oh, wow. Checkpointing.
Yes. Built-in native checkpointing. Which means if your agent is on step 14 of a 15-step process and the API times out, your custom while loop implementation just crashes and loses all memory of steps 1 through 17.
Right.
But LangGraph simply pauses. It has the state saved right up to step 13. You can wake the graph up 2 days later and resume it from the exact node where it failed. That is the superpower you are buying when you adopt the framework.
Okay, that is huge. But that superpower comes with a cost. Promer noted that LangGraph is widely considered the most mature option, with the best documentation and a massive community. But the reality of that maturity is rough. In the 6 months prior to him running this experiment, LangGraph shipped 3 breaking changes.
Yeah, that's tough.
3. In a 6-month window, if I am a CTO, shipping breaking changes that force my team to refactor our core routing logic every 8 weeks is like the opposite of mature.
Well, this raises a fascinating point about what the word maturity actually means in the context of AI tooling in 2026. Because in traditional enterprise software, like a Postgres database or a Spring Boot Java application, mature means stable. It means ossified. You install it, and you don't touch the core syntax for a decade.
Sure.
But in this hyper-accelerated AI space, mature simply means the framework has enough real-world users hitting real-world walls that the maintainers are being forced to rapidly iterate based on actual pain points.
So the breaking changes are actually a symptom of survival.
Exactly. When LangGraph first launched, the state management was relatively simple. But as enterprise teams started building graphs with hundreds of nodes, pushing massive amounts of context through the system, the maintainers realized the underlying state schema had to change. They had to support different persistence layers, like switching from Squillet to proper Postgres backends.
Thanks.
Those breaking changes were incredibly frustrating for a team trying to maintain a code base, but they were the necessary growing pains of a framework actively adapting to the brutal reality of production AI. It forces you to draw every data flow explicitly, and as the requirements for those flows got more complex, the syntax just had to evolve.
Okay, so we've looked at Pydantic AI's type safety and LangGraph's explicit graph routing. Let's shift slightly sideways before we move up the abstraction ladder. We have to talk about LlamaIndex agents. Now, LlamaIndex is famous for its RAG capabilities, retrieval, augmented generation, but they've built agent primitives directly on top of that heritage.
Yeah, this is a highly specialized contender. If you look at the architecture of a LlamaIndex agent, it is fundamentally shaped by a retrieval-first mindset. Everything is oriented around parsing documents, chunking text, creating vector embeddings, and routing queries to the correct index.
It seems like an incredible tool if your core problem is, we have a mountain of proprietary PDF contracts, and we need an agent to navigate, retrieve, and synthesize that specific legal knowledge.
Yes, in that specific domain, it brings incredibly powerful tools to the fight. But this is where Promer's experiment is so revealing. When you force LlamaIndex to build a generic 3-step research agent that isn't just about querying a static document store, but involves orchestrating external web searches, formatting data, and making autonomous decisions, it starts to feel a bit awkward.
It's the classic, when all you have is a hammer, everything looks like a nail scenario.
Precisely. You are trying to use a framework optimized for searching vectors to manage complex multi-step business logic. It can probably do it, but you are really fighting the grain of the framework.
Right. Okay. Let's make a massive jump up the abstraction spectrum. We are leaving the world of explicit graphs and type-checked functions and entering the world where we start treating the AI like people. Contender number 4. AutoGen, backed by Microsoft.
This is where the paradigm shifts entirely. AutoGen frames everything, and I mean literally every computational step, as a conversation between agents. You don't define a graph, you define personas.
Personas, okay.
Yeah. You define a user proxy agent that acts on behalf of the human and an assistant agent that acts as the AI. You put them in a virtual chat room, give them a task, and they literally send text messages back and forth to each other until the task is complete.
And obviously, being Microsoft, this has massive enterprise support. It integrates beautifully with Azure. But I have to push back on this core philosophy. When AutoGen frames back-end execution as a conversation, does that actually map well to enterprise architecture?
It's a great question.
Because think about how corporate problem solving works. Yes, humans jump into a Slack channel, we debate, we resolve ambiguity through conversation, so it feels natural to model AI that way.
Yeah.
But if I need an agent to securely query a SQL database, extract specific financial records, and format a rigid JSON payload to send to a billing API, why on earth does it need to chat about it with another agent? Isn't that just introducing massive linguistic ambiguity into what should be a deterministic data pipeline?
You have just articulated the exact central tension that Palmer's experiment exposed with AutoGen. Framing computation as conversation is a brilliant mental model for open-ended, creative problem solving. If you want two agents to brainstorm marketing copy, a conversational paradigm is perfect. Agent A writes a draft, Agent B critiques it, Agent A revises it.
Right, that makes total sense.
But for rigid data pipelines, it is incredibly dangerous.
How does the system even know when the job is done? If they are just chatting, what is the trigger to move to the next system state?
That is exactly the vulnerability. In AutoGen, loop termination often relies on the LLM generating a specific string, like the word terminate.
Oh, yes.
You are relying on a non-deterministic language model to correctly deduce that the conversational goal has been met, format the data correctly, and remember to append the magic word to end the while loop. If the model gets confused or decides to ask a clarifying question instead of terminating, you end up with infinite loops of agents just politely agreeing with each other while your API bill skyrockets.
Which brings us right back to that 3:01 a.m. Sunday nightmare.
Exactly.
Okay, let's look at the framework that takes abstraction to the absolute limit for the sake of developer experience. CrewAI. This framework is heavily anthropomorphized. You aren't drawing graphs, you aren't managing state, you define a crew. You create agents with specific roles, like senior financial analyst. You give them tasks, and then you just hit go.
It is the ultimate meal kit for AI development. Palmer noted that the developer experience on day one is simply unparalleled. You can get a multi-agent CrewAI system up and running, executing complex workflows in roughly 30 lines of Python code.
30 lines, that's it.
That's it. It genuinely feels like magic. It completely abstracts away the complex reality of how the language models are actually being chained together.
But magic always has a price, right? And the catch with CrewAI is significant. It completely defers state management back to you, the developer. It handles the routing like. It knows when the researcher agent should hand off to the writer agent. But it doesn't strictly enforce or manage the memory of what happened inside those steps.
And we are going to dive really deeply into what that means for state management shortly, because it is the pivot point of the entire experiment. But to contrast CrewAI, we have to mention our final contender, number 6, OpenAI Swarm.
Yes, Swarm. This one is fascinating precisely because of what it isn't. It is incredibly lightweight. It strips away almost all the heavy abstractions of CrewAI or LangGraph. It basically just consists of two primitives, agents, and the concept of a handoff so agent A explicitly passing execution control to agent B along with a context payload.
It is vital to understand how OpenAI themselves position Swarm. They are explicitly stating that it is an educational reference implementation. It is a blueprint.
It's like they handed you the schematics for an internal combustion engine and said, look, here is elegantly how the pistons and the spark plugs interact in theory. Please, for the love of God, do not put this in a chassis and drive it on the highway.
Exactly. It lacks the robust error handling, the persistent memory architectures, and the complex graph validation that you absolutely need for an enterprise application. It is brilliant for learning the mechanics of agentic handoffs, but treating it as a production-ready framework for standardizing enterprise architecture is a massive mistake.
Okay, so we have our 6 contenders on the table. We have the strict type safety of Pydantic AI, the explicit graphs of LangGraph, the specialized RAG tools of LlamaIndex, the chat rooms of AutoGen, the high-level magic of CrewAI, and the educational blueprint of OpenAI Swarm.
Quite the lineup.
Right. And looking at that list going into this experiment, you would naturally assume that after forcing them all through the identical 3-step research task, they would rank neatly from 1 to 6. You'd get a clear winner, a clear loser, and a gradient in between based on features and ease of use.
But that isn't what happened at all. When the code was actually written, when the agents were actually subjected to network latency and parsing errors, they didn't form a hierarchy.
No, they fractured. This is the big finding, the core realization of Promer's entire deep dive. The moment these 6 frameworks were put under load, they aggressively split into 2 distinct factions based entirely on one single architectural design choice. Everything else, the syntax, the enterprise backing, the RA features, it all just faded into the background. It all came down to one thing: state managed.
State management. This is the fault line running through the entire AI engineering landscape in 2026. Promer realized that frameworks naturally divide into Camp 1, strong opinions on state, and Camp 2, state deferred.
And if we want to really grasp why this matters, we have to unpack what state actually means in the specific context. Because I know CTOs and engineering leaders understand stateful versus stateless applications, but when we introduce large language models into the mix, the engineering reality of state management becomes uniquely hostile.
It really does. Let's break down the physical reality of what is happening when an agent runs. At their core, LLMs are stateless APIs. When you send a prompt to GPT-4 or Claude, the model processes the tokens, generates the output, and the moment that API connection closes, the model retains zero memory of the interaction.
Right. It is completely amnesiac.
Exactly.
So if I am orchestrating a complex multi-step task like our 3-step research agent, some component in my system has to constantly catch the output of the LLM, serialize it, store it somewhere, and then inject that historical context into the prompt for the next step.
Yes, that persistent memory, that ever-growing ledger of what the user asked, what tools we have called so far, what raw data those tools returned, and what partial conclusions the LM has drawn, that is the state. And the divide between these frameworks is entirely about whose job it is to maintain that ledger.
Okay, so let's look at Camp 1, strong opinions on state. There's LangGraph and Pydantic AI. These frameworks take the stance that handling memory, maintaining the state ledger, and ensuring type safety must be handled explicitly at the framework level. The framework itself provides the rigid, inescapable structures to hold that memory.
Right. In LangGraph, you cannot even begin to write your agent logic until you define a type hedict or a Pydantic model that represents the absolute totality of your agent's memory. If step 1 of your workflow involves extracting a list of URLs from a search engine, the framework demands that you explicitly define a variable in your state schema called extractors with a type hint of a list of strings.
Wow, so you have to know exactly what you're storing up front.
Yes, the framework enforces that structure at every single transition between nodes.
It is forcing you to be meticulous. And then there's Camp 2, state deferred. This is where we find CrewAI and OpenAI Swarm. These frameworks handle the agentic routing beautifully. They manage the prompts. They tell agent A to talk to agent B, but they throw the responsibility of remembering what just happened completely back over the wall to you.
Which is incredibly alluring at first. I mean, it is exactly why CrewAI boasts that 30 lines of code on-ramp. When you don't have to spend 3 hours designing a rigorous state schema and writing reducer functions to manage how memory updates, you can move incredibly fast. You just give the agents their instructions and watch them go.
But wait, if CrewAI defers the state, how does it remember anything across a long workflow?
It relies heavily on just passing the raw conversational context back and forth. It just appends the string of what happened into the prompt for the next step.
So it's a giant string of text.
Basically, yeah. And if you want true structured persistence, say you need to save an intermediate JSON object to a database before moving to the next step so other backend systems can read it. CrewAI essentially says, great idea, you should write the Python code to connect to your database and handle that inside a custom tool.
Which is really just a polite tech industry way of saying, that sounds like a you problem.
Exactly.
They do all the glamorous work of wrapping the LLM API calls, but the tedious, difficult, essential work of data persistence and reliability, that is on the developer to build from scratch.
That's precisely what it means. And this single binary choice to explicitly force state management or to defer it, it drives literally everything downstream. It affects your computational costs, it affects your latency, and most importantly, it dictates your debuggability when the system inevitably fails.
Which brings up a massive qualitative trade-off, because it feels like Camp 2, the deferred state camp, is designed to make you look like a genius by Friday afternoon. You pull down CrewAI, you write 30 lines of code, the agents talk to each other, the demo works flawlessly, and the CEO is thrilled.
Yep.
But Camp 1, the strong opinions on state, is the architecture that actually saves your entire weekend when that exact same agent hallucination happens in production on a Sunday night.
Yes. Because under heavy, sustained production load, the probability of an LLM doing something unexpected or a third-party API timing out approaches 100%. Your agent will fail. Step 2 of your process will eventually crash.
It's guaranteed.
It is. The question isn't how to prevent failure. The question is how your framework allows you to recover from it.
And this deep divide regarding state completely upended Promer's initial expectations going into the experiment. He went in with a set of assumptions based on years of traditional software engineering, and those assumptions just got brutally dismantled when he actually started writing the code and watching the failures happen.
Yeah, and this leads us to the most fascinating part of his write-up, the honest practitioner beat, or basically what I got wrong.
It is incredibly refreshing when a practitioner of Promer's caliber openly details where their intuition led them astray. It gives everyone else permission to reevaluate their own biases.
Mm-hmm. Definitely.
So his prime example is centered directly on LangGraph and its notorious reputation for boilerplate code. If you look at Reddit or developer forums in 2026, the primary complaint about LangGraph is the verbosity. Promer fully expected that the sheer volume of boilerplate required to stand up a simple LangGraph agent would be an absolute deal breaker, especially for small, fast-moving teams. He assumed it would be too heavy, too slow to iterate on.
Which is a very logical assumption. I mean, in traditional web development over the last decade, we have waged a war against boilerplate. We have spent years building frameworks like Next.js or Ruby on Rails, whose sole purpose is to hide boilerplate code so developers can focus strictly on business logic and move faster.
Exactly. But the reality he found in the mud pit, the boilerplate wasn't a burden at all. It was a lifeline. That explicitly typed state graph earned its keep the very first moment things went sideways.
We really need to explore the underlying philosophy of boilerplate here because AI fundamentally shifts its value proposition. In traditional software, where the compiler ensures the code runs predictably, boilerplate is just redundant setup.
Right.
But in Agentic AI, where the core engine, the LLM, is a chaotic, non-deterministic probability matrix, boilerplate serves a completely different function. It isn't redundancy, it is the rigid physical infrastructure. It's the guardrails keeping the car on the track when the driver decides to go blindfolded.
Let's make this incredibly concrete with a hypothetical scenario, because I want to make sure I really grasp the operational difference here. Let's go back to our 3-step research task. Step 1. The agent searches the web via an API and finds 10 relevant articles. Step 2. The agent reads those 10 articles, processes the text, and extracts key financial metrics into a JSON dictionary. Step 3. A final agent takes that JSON dictionary and formats it into a beautiful markdown executive summary.
A very standard, high-value enterprise workflow, exactly the kind of thing teams are trying to automate every day.
Right. So let's trace the execution. Step 1 works perfectly. The API returns the articles. Step 2 starts reading them. It successfully extracts the revenue numbers, but the LLM decides to get creative. Instead of formatting the extracted data as the required JSON dictionary, it hallucinates the format and outputs a bulleted list.
Typical.
So that bulleted text hits step 3. The parsing logic in step 3 is expecting a JSON key called revenue. It encounters a bullet point instead, throws an exception, and the entire agentic system crashes.
A classic, unavoidable AI failure mode. The model just forgot the schema instruction.
So how do you fix this as the developer on call? If you are using a system where you deferred the state, like CrewAI, the agent just crashed, the memory of step 1 and step 2 might be completely gone, evaporated from RAM because the Python process died.
Yep. And because you didn't have explicit framework-level state persistence to fix it and test your fix, you have to restart the entire workflow from the beginning.
Which means you have to pay the API cost to run step 1 again. You have to wait the 3 minutes and pay the LLM token costs for step 2 to read 10 articles all over again, just to see if your newly tweaked prompt for step 3 actually fixes the JSON parsing issue.
It's agonizing.
And if it fails again, you run the whole expensive slow loop again.
This is exactly where the developer experience truly diverges between the high abstraction frameworks and the explicit state frameworks. In LangGraph, because you have that hated boilerplate explicitly defining the state graph, the system automatically saved the state to the database after every single node. The framework knows exactly what the output of step 2 was, even though it was a malformed bulleted list instead of JSON.
Wait, so you can literally pause the graph, you can open up your tracing tool, Inspect the explicitly typed state, see the exact malformed string that step 2 generated, manually correct it to a JSON object, or tweak your parsing logic and then resume the workflow from that exact point.
Precisely. You don't rerun step 1, you don't rerun step 2, you don't waste the time or the API tokens. You inspect the state, you fix the mismatch, and you continue execution. That verbose boilerplate was just the upfront premium you paid to buy yourself a time machine for when the LLM inevitably derailed.
The time machine, that's exactly what it is.
Yeah. Prommer realized that in production, debuggability is exponentially more valuable than the initial speed of writing the code.
That is a profound realization. It really makes me wonder, is there a danger right now that we as an engineering industry are so seduced by the magic of AI? The promise of just tell the crew in plain English what to do and it happens, that we are abandoning standard, hard-won engineering principles. It sounds like Prommer realized he actually missed standard software engineering rigidity.
That is perhaps the most important philosophical takeaway from the entire experiment. I mean, we have spent the last 30 years building paradigms, strong typing, explicit data contracts, immutable state to make software deterministic and reliable. Suddenly, we introduce an inherently non-deterministic component into the stack, and our collective first instinct was to just throw away all our rigid tools and just talk to the system.
Yeah.
Prommer's experiment is a stark reminder that the more chaotic and unpredictable the core engine is, the more rigid and heavy the chassis needs to be to contain it. Explicit state management, rigorous type checking, hard error boundaries, these aren't legacy concepts slowing us down. They are the only proven way to build production AI systems that don't collapse under their own weight. So if boilerplate is actually a superpower in this context, and deferring state is actually a massive hidden risk for production stability, where does that leave you, the listener, trying to make a choice? Let's get to the final verdict of Prommer's massive head-to-head evaluation.
The landing point of this experiment is incredibly clear, but it requires nuance to apply correctly. Out of the 6 frameworks tested, 2 rise to the absolute top. They essentially tie for first place as general-purpose orchestrators, LangGraph and CrewAI.
A tie. But wait, they live in completely opposite camps. LangGraph is Camp 1, heavy boilerplate, strong explicit state. CrewAI is Camp 2, highly abstracted deferred state meal kit. How can 2 fundamentally opposed architectures both be the winner?
Because they both absolutely excel at their specific win conditions, and both are genuinely production-worthy for a team standardizing in 2026, provided the team understands exactly what technical debt they're buying into.
Okay, let's break down those win conditions for the CTO. Let's start with CrewAI. Its win condition is entirely about velocity. It is speed to first agent. It provides a gentle, welcoming on-ramp that doesn't require your developers to learn graph theory or finite state machines. If your priority is rapid prototyping, if you have a mandate to prove business value to skeptical stakeholders by next Tuesday, CrewAI gets you there.
Exactly. It abstracts the complex orchestration away so your team can focus purely on the business logic, the tool creation, and the prompt engineering. And for many startup teams or internal innovation labs, that velocity is the most critical metric. You can't worry about standardizing state management for an architecture that might pivot in 3 weeks anyway.
That's a fair point. But then you have LangGraph's win condition. It wins on explicit control, type state persistence, and maturity when diagnosing complex multi-step failures. It is the choice for when the prototype phase is over, the budget is approved, and now this agentic pipeline needs to run 10,000 times a day, asynchronously, without human supervision.
Right. It gives your DevOps team the exact tools they need to audit why an agent made a specific routing decision at a specific node, and the ability to resume workflows when external APIs time out.
So the tiebreaker between LangGraph and CrewAI isn't about which framework has better Python code in its repository.
No, the tooling is excellent in both cases. The tiebreaker is your engineering team's internal psychology and business priorities.
So the remaining 4 contenders, where do they sit in the final verdict? Prommer is very clear in his write-up here. They are positioned strictly as situational runners-up. They're not the top universal picks for a general-purpose orchestration standard.
And it is crucial for architectural leaders to understand the danger of standardizing on a situational runner-up for general-purpose use. You end up fighting the framework every day.
Let's run through them so everyone has the complete map. Pydantic AI. Prommer's verdict. You choose this only if your team practically lives and breathes typed Python. If your entire backend is already a massive FastAPI monolith, heavily invested in the Pydantic ecosystem, adopting Pydantic AI makes perfect sense. The impedance mismatch is 0.
But if your team is more polyglot, or leans heavily on data scientists who write looser, imperative scripts, forcing them into strict Pydantic models for every agent interaction is going to cause massive friction.
Right, and LlamaIndex agents, the verdict. Choose this only if your agent's workflow is almost entirely focused on retrieval, like if it's fundamentally a massive RAG application. If the agent's primary job is synthesizing knowledge from vector databases, LlamaIndex is unmatched.
Yeah, but if you try to use it to build a complex reasoning system that orchestrates Jenkins pipelines, sends emails, and updates CRM databases, you are using a hammer to drive a screw. It can be done, but it is not what the internal architecture was explicitly designed to excel at.
AutoGen. The verdict here is very specific. Choose this if you are a strictly Microsoft enterprise shop. If you are deeply embedded in the Azure ecosystem, utilizing Azure OpenAI services, and the conversational multi-agent chat paradigm aligns with how your existing internal services communicate, it's powerful.
Otherwise, the overhead of managing linguistic ambiguity and loops might be completely unnecessary.
And finally, OpenAI Swarm. The verdict is simply to trust OpenAI's own explicit positioning. Treat this as a learning reference. If you have junior engineers who need to understand the underlying mechanics of how context is passed during an agent handoff, have them study the Swarm source code. But it is absolutely not a production choice.
No, definitely not.
So if I am trying to synthesize this entire 6-framework mud pit test for you, the listener, the CTO, and the hot seat, you have to look in the mirror and ask a fundamental question about your engineering culture. Are we a move fast and break things team that needs to validate ideas at lightning speed, accepting that we will have to build our own robust state management later? If yes, look at CrewAI. Or are we a measured twice cut once team that operates in a complex environment where silent failures are catastrophically expensive, and we are willing to pay the upfront tax of boilerplate and a steep learning curve to buy long-term auditability? If yes, look at LangGraph.
That is the perfect distillation. Neither architectural choice is inherently wrong, but being blind to the trade-off you are making regarding state management is fatal.
It is such a clarifying way to look at the landscape. It cuts right through the hype. But here's the thing. This massive head-to-head evaluation, this entire decision matrix we just spent an hour dissecting, this was just the beginning of the journey. As Promer outlines at the end of his article, picking the orchestration framework is literally just the starting line for Season 2 of CTAIO.dev.
Which really highlights the immense compounding complexity of what engineering teams are dealing with right now. Framework selection is foundational, it dictates your state management, but it is only step one. Now that you've chosen your vehicle, whether it is the heavy LangGraph tank or the nimble CrewAI dune buggy, you have to decide how you are going to drive it.
Exactly. He teased the upcoming content for the rest of Season 2, and the engineering depth looks intense. First up, once the framework is selected, he is going to be testing 3 specific multi-agent topologies in production: the monolith, the handoff, and the swarm.
And to briefly connect today's topic with that tease, architecture doesn't stop at the framework. You now have to architect how your agents interact with each other. Do you build one massive monolithic agent with a 10,000 token system prompt that tries to do everything itself?
Probably a bad idea, but people do it.
They do. Or do you use a sequential handoff topology where a distinct researcher agent does a task and formally passes a structured result to a distinct writer agent? Or do you build a true swarm topology where multiple agents operate in parallel, negotiate outcomes dynamically, and resolve conflicts? Each of those topologies stresses your chosen framework's state management in entirely different ways.
And then the piece I am most excited about, because it ties directly into our 3.00 AM failure scenario, he is doing a massive head-to-head comparison of 4 agent observability tools: Langsmith, Helicone, Phoenix, and Langfuse, because as we discussed, these non-deterministic agents are going to go rogue, and when they do, you need telemetry. You need to be able to see inside the black box.
Observability is the absolute natural consequence of everything we just talked about regarding state. Think about it. If you chose a framework like CrewAI that defers state, your reliance on an external observability tool becomes absolute. You cannot survive without it. You need tools that intercept the API calls at the network layer to trace the LLM inputs and outputs, monitor the token cost per agent step, and visualize the execution paths in flame graphs. In 2026, agentic observability is no longer an optional nice-to-have. It is mandatory, mission-critical infrastructure.
So, the agentic orchestration landscape has truly matured. We have officially moved from the era of toy scripts and weekend hackathons to the era of serious, rigorous software engineering. Frameworks like LangGraph and CrewAI are leading the charge, but they're dragging us into a future that requires deep architectural thinking about state, memory, and non-determinism.
The muddy waters of the AI landscape are starting to clear, but only for those teams willing to actually do the hard engineering work of building the bridges rather than just trusting the magic.
I want to leave you, the listener, with a final, lingering question to ponder as we wrap up this deep dive. We started by talking about the comfort of traditional software engineering, the clarity of an explicitly typed code base, where if something breaks, the compiler gives you a stacked trace pointing exactly to the broken line of logic. It is like an X-ray showing exactly where the bone is broken. And we've seen how incredible frameworks like CrewAI are becoming wildly successful, precisely because they abstract away the complex, messy reality of state management. They hide that X-ray from the developer to make the initial build process faster and more intuitive. But as the industry standardizes on these highly abstracted magic frameworks, what happens to the next generation of software engineers?
It's a great question.
Are we risking a future where developers are no longer engineers who fundamentally understand the flow of data, memory management, and system state, but merely become prompt assemblers? If we rely entirely on the framework's magic to route the agents, parse the outputs, and defer the state, what happens when that black box finally breaks in the deepest, darkest part of the production mudkit, and there is no one left on the engineering team who actually knows how to inspect and fix the underlying graph?
Yeah, you're basically going to have to build it from scratch, which is kind of terrifying.
Something to think about the next time you decide to let a framework handle the memory for you. We will catch you on the next deep dive.
Hello again. That's it for the Season 2 opener of CTAIO Labs. So the headline of the 6 frameworks, LangGraph and CrewAI separate from the pack, and they're close. CrewAI gets you to a working agent fastest, the gentlest on-ramp. LangGraph gives you explicit control and type state for when things go wrong. The tiebreaker isn't the tool, it's your team's priority. The other 4 are situational. Pydantic AI for type Python shops, LlamaIndex, when it's mostly retrieval, AutoGen for Microsoft enterprises, and Swarm for learning, not production. This season, we keep going on agentic orchestration. Next, I take 3 multi-agent topologies: monolith, handoff, and swarm. Into production show, where each one breaks, then put 4 agent observability tools head-to-head. Subscribe on Apple Podcasts, Spotify, or YouTube so you don't miss it. And if this was worth your time, share it with someone who's building agents. I'm Thomas Palmer. This is CTAIO Labs. See you next episode.